pressure?
One more.
Oh, okay. Just hand that one back. Something back here needs to be in. Okay, type 3 certification is low pressure equipment. Typically, the only low pressure equipment you'll be ever working on are chillers. And really centrifugal chillers or CentriVac chillers are your only really low pressure chillers. They make other chillers that run those types of compressors right there. They're a high pressure chiller system just like an air conditioner. But your CentriVac and your centrifugals are low pressure chillers. So technicians maintaining, servicing, repairing, or disposing of low pressure appliances must be type 3 technicians or universal technicians. Same rules apply as of November 14th, 94. The sale of CFC and HFCFC refrigerants have been restricted to certified technicians, just like type 1, type 2, same in type 3. Same thing, if EPA regulations change, it's your responsibility to keep up with the changes. If you're just a type 3 and they make a change in type 3, you gotta keep up with the changes. Leak detection. Because low pressure systems operate below atmospheric pressure, they actually operate in a vacuum. Leaks in the gaskets or fittings will cause air and moisture to enter the system. When you're dealing with low pressure systems, you're going to have what they call a purge unit setting on the chiller. And it's basically just a little condensing unit that sucks the non-condensables off the top of the condenser. And it just sucks them out of there and purges them back out into the atmosphere. The most effective method of leak checking and charging low pressure refrigerant units is to pressurize the system with the use of controlled hot water or heat blankets. But you got to make sure when you're working on these things that you don't put too hot of hot water into the chiller. And we got a picture of a chiller in here. Chillers have what they call a rupture disc on them. If you get the hot water too hot and you get too much pressure in the chiller, the rupture disc blows off and you lose hundreds of pounds of refrigerant. These things blow off at 15 pounds of pressure because they only run about 8 pounds. Normal operating conditions, they'll run 8 to 10 pounds of pressure on the high side, and they'll run at minus 10 inches of mercury on the low side. So you can put warm water in there. We never go over 100 degrees. Typically we try to stay around 75, 80 degree water. That'll get your pressure right up to about 12 psi. And that's pushing it close. But and it's really hard to leak check at 12 psi. Not a lot of pressure there to force that refrigerant out. So leak checking a low pressure system is really hard. It says when controlled hot water or hot water blankets are not feasible, use nitrogen to increase the pressure. If you got to do that, you can take the rupture disc out, block it off, put nitrogen in the system. If you just can't find it, the only thing you got to do is remove what refrigerant's in there, block the rupture disc off, pump it up with nitrogen to 70, 80 pounds of pressure, and take your reading. But when pressurizing a system, do not exceed 10 psi. Exceeding 10 psi can cause a rupture disc to fail. When leak testing a hot or a water box, be certain that water has been removed before placing the leak detector probe through the drain valve. To leak check a test tube, use a hydrostatic test tube kit. Systems with open drive compressors are prone to leaks at a shaft seal. There's not a whole lot of open drive compressors out there anymore. I know you've all seen an air compressor, like an old gas station that had a compressor motor and then a electric motor with fan belt. Electric motor spun the big wheel, that's an open drive system.
Maybe down in DC somewhere or over in Baltimore somewhere, you
That-
might find one.
Yeah, that's possible. But on an open drive system, the shaft comes right out the side of the compressor unit. There's just a seal there, and that refrigerant is on the other side of it. Those seals go bad, they constantly leak around there. But there's not too many of those around anymore. EPA regulations require that all comfort cooling appliances containing more than 50 pounds of refrigerant be repaired when the annual leak rate exceeds 15%, just like type 2. Type 3 is the same thing. EPA regulations require that all commercial and industrial process refrigerant containing more than 50 pounds of refrigerant be repaired when the annual leak rate exceeds 35%, same as type 2. So a lot of these requirements carry over from type 1 to type 2 to type 3. Recovery techniques. A recovery unit's high pressure cutout is set for 10 psi when evacuating the refrigerant from a low pressure chiller, and a rupture disc when the low pressure recovery vessel relieves at 15 psi. So if you're recovering these things here, the recovery unit's high pressure cutout is set for 10 psi just because the ruptured disc on the chiller will rupture at 15 psi. When you're in almost every chiller I've worked on, it fluctuates with that 10 to 12 psi, and it's scary. They seem to hang in and stay right there. I've never had one blow off yet, but I've heard stories of them happening. It's not pretty when they do. Refrigerant recovery from a system using R11 or R123 starts with liquid removal and then followed by vapor recovery. Just because with these things, you got to pull as much liquid out as you can from the amount of refrigerant that's in there. Most chillers are going to hold 200, 300, 400 pounds of refrigerant. So if you're trying to recover 400 pounds of refrigerant in a vapor form, you'll be there for a month trying to get it all boiled off and out. So recover as much liquid as you can. A substantial amount of vapor will remain in the appliance after all liquid is removed. Says, for instance, an average 300-ton or 350-ton R11 chiller at 0 psi still contains 100 pounds of vapor. And that's where you've got to heat that thing up. You get as much of the refrigerant out of it as you can. You can then heat those hot water tubes up. You can heat those water tubes a little hotter because you got as much of the liquid out. You just got to keep getting that vapor and working it back to the system to get it out of there. Sometimes you got to pull from multiple points in the system. You pull from one port here for a while, and you move it and pull from another section, and then move and pull from another section, come back to where you was originally at. Do that 3 or 4 times so you get everything out of these things. They're a bear to work on. When you're pulling refrigerant out, you've got to keep water circulating through those tubes. When I show you the pictures here, you understand. If that water in those tubes just lay in there, when you're evacuating refrigerant, you're making that refrigerant boil. You're vaporizing it. When it's boiling, it's getting colder and colder and colder, well below 0. And there's a tube of water sitting around it. It's going to freeze that tube solid and end up busting it. Then you got a real mess. So you always got to make sure you got either all the water out of it, or you got your water constantly circulating while you're evacuating a unit out. Most low pressure recovery machines utilize water-cooled condenser that is connected to the municipal water supply. Typically for these systems, The little recovery machines that we use won't cut it for these things, because these machines are just like an air conditioning compressor. They rely on that vapor coming back over the compressor to cool the motor down. You're pulling such little vapor and this thing's running for such a long time, motors overheat, burn up. So they use just municipal water, hook it up to a spigot, hook a garden hose onto it, it flows water through a water-cooled condenser to keep that compressor cool. If a chiller is suspected of tube leaks, the water side of the evaporator and the condenser should be drained prior to recovering the refrigerant. If it's got tube leaks, typically, until it goes flat, the water won't get into the refrigeration circuit. It'll just, there's enough pressure there to keep the water out, lets the refrigerant flow out. Unless you have a huge split and it dumps all the refrigerant out, then you got a real mess when you got water in your refrigeration circuit. We got Gaithersburg High School. We did the school, another contractor started it, we took it over, and they put water source heat pumps that had plate heat exchangers up in the unit. And so far, they've had 9 of them fail. The manufacturer didn't put differential pressure switches on the inlet and the outlet of the heat exchanger to prove water flow through the heat exchanger. Water wasn't flowing through it. The compressors were running R410, minus 64 degrees. Water and minus 64 don't mix. Busted the heat exchangers, lost all the refrigerant, and all the water flowed back into the refrigerant circuit, filled the compressor up with water, filled the receivers up with water. So they had to come in and tear the entire refrigerant circuit out of this unit and rebuild it. New compressor, new receiver, new coils, new everything.
Yeah, see, I have one of the buildings I had over here in White Oak with it's not the same setup, but you had perimeter heat pumps basically, and the shell and tube and stuff. What happened in that building is that the water system was never kept right at the first part, and they had too many different types of metals. So you had the electrolysis going on. So after a while, they started having to change units as they were slugging themselves because the shells would give up, and then the water would go through and slug the compressor, and that was it.
Yep. Yeah, this company's out of Atlanta, Georgia, and the first round we had four units that lost 4 compressors, and they sent their techs from Georgia up here right around Thanksgiving. Everybody knows how cold it was right around Thanksgiving. They were hating life. They were up here working up on the roof in the cold, and these things there's 4 compressors, so there's 4 circuits in a unit. But instead of putting what they call your evaporator coil, instead of putting a stacked coil, it was one coil that were all intertwined together. So to replace that coil, they had to pull all the refrigerant out of all 4 circuits, and then pull that whole coil back, put a whole new coil in, hook all 4 circuits back up, rebuild the entire first circuit, pull vacuums on everything, recharge everything. It took them like 2 weeks to do one unit. They were here for over a month. And then they thought they had it fixed, and about 3 weeks later, same thing happened again, but they lost 5 units that time. They come to find out they didn't have the differential pressure switches. The compressor didn't know that water wasn't flowing. And anytime you have a system that you're dealing water cooled, the water's got to flow. If the water's not flowing, the compressor cannot run. And they missed them.
It gets hot as hell.
Shouldn't the technicians have seen that?
Yeah, they should have. It wasn't my guys, which I'm glad.
Yeah.
We contracted a startup company to come in and start these things up. Because I mean, each piece of equipment is probably $60,000 or $70,000 per piece. And that wasn't, it was a liability, there were 17 of them in there. We're not gonna take that liability. So we hired a factory
All
trained, factory trained startup company. And the factory missed it, the startup company missed it. So Montgomery County Schools not too happy with us. It wasn't our fault, but they're not too happy with us because technically it's our job. We should have.
You hired the subcontractor.
We hired them, and we should have probably looked over their shoulder more. Hindsight, we see it now, but we learn from it. The next job we do, we'll have somebody with the startup company watching what they're doing. ASHRAE Guidelines 3-1996 states that if the pressure in the system rises from 1 millimeter Hg to above 2.5 millimeters Hg during a vacuum test, the system should be leak checked. I've never seen that question on there. It's highlighted though, so just put that in your head. And basically what they're saying is when you put a vacuum on it and you got it to you think you have it to the vacuum, that your required vacuum, if it moves a millimeter to 2.5 millimeters during the test, typically the test is an hour long. Set it on there, you let it set for an hour. If it doesn't budge, you're good. If it budges, then you gotta leak check the system. A temperature of 130 degrees should be attained when removing oil from a low pressure system. Fewer refrigerants is contained in the oil at the higher temperature. Basically, all these systems are going to have sump heaters that are in the bottom of the compressor. They keep the oil hot. Just make sure they're on. Above 135 degrees, all that refrigerant will be boiled out of that oil. Recharging techniques. I know this is on there, he said. When you're recharging these systems, you add the refrigerant to the lowest point of the system, and you never introduce liquid refrigerant into a deep vacuum, because it'll cause it to boil at very low temperatures. You put vapor into the system until you've reached 16.9 inches, or 16.9 PSI, really. They got inches of vacuum. But you reach 16.9 PSI, or a saturated temperature of 36 degrees. That way you're above the boiling point of this refrigerant. If you just dump a bunch of liquid inside, you're going from a high pressure little can into a great big system. That pressure is going to drop off real fast. It's going to flash off to a vapor. If there's any water standing in those tubes, it'll freeze them up in a heartbeat. So you always introduce it as a vapor until you build your pressure up. Once you get your pressure up, you can dump liquid into it. Refrigerant recovery and recycling equipment manufactured after 1993 must be certified and labeled by the EPA approved. Equipment testing organization must meet EPA standards. This is new to their law, though. All equipment now must have low loss fittings. These low loss refrigerant fittings. So by code, by law, all your gauges should have low loss fittings on them nowadays. They still sell hoses without them, but they sell the little fitting that fits into the hose to make it a low loss fitting. That was something that just got added not too long ago, that you got to have those low loss fittings. I think I have a up here. Using recovery or recycling using recovery or recycling equipment manufactured or imported before November 1953, 1993, has to reach 25 inches of mercury. Using refrigerant and recycling equipment manufactured after 1993 must meet 25 millimeters. And then it says absolute, so it's got to go to 25 millimeters of mercury. Big difference between inches and millimeters. I mean, 25 inches is that much. 25 millimeters is that much, you know. So there's a big difference there. For chillers, they want these things pulled down into a deep vacuum just because they run in a vacuum. Once the required vacuum has been achieved, the technician should wait a few minutes to monitor the system for pressure. If pressure rises, indicating that there is refrigerant remaining in the system, recovery must be repeated. When leaks in the appliance make evacuation to the prescribed level unobtainable, the appliance should be evacuated to the lowest obtainable level prior to a major repair. If you got leaks, you're never going to get down to 25 millimeters. It's not going to happen. You just pull it as much as you can, get as much of it out, and go along with the repair. The use of large vacuum pumps may cause trapped water to freeze. Again, it's better to flow that water through there instead of draining it. You can never drain all the water out. As long as your condensed water pumps are moving, you're always going to be flowing water through it. During evacuation, a system with large amounts of water may be necessary to increase pressure by introducing nitrogen to counteract freezing. If a strong odor is detected during the recovery process, a compressor burnout may have occurred. When recovering refrigerant from a system with an expected compressor burnout, watch for signs of contaminants in the oil. Again, if it's too bad, you don't have to recover that refrigerant. If it's a burnout, really burnout, you really don't have to recover it. You can let it go. Yep. I don't. I guess they're figuring that it's not going to be that many of them, but they say you don't have to recover it. Because chillers using refrigerants such as R11 and R123 operate below atmospheric pressure, they require a purge unit. The primary purpose of the purge unit is to remove non-condensables from a system. A centrifugal chiller's purge condensing unit takes its suction from the top of the condenser, removes air and other non-condensables from the system, and returns the refrigerant back to the evaporator. And just, if you ever start working around chillers, you'll hear them every once in a while. Those little things will kick on, and then when they kick off, you'll hear them spitting out air. They'll dump all the refrigerant they can back into the system, then they'll spit the air out. I've never really figured out how they work, but they do work. Although high efficiency purge units discharge a low percentage of refrigerant into the air they remove, frequent purging and substantial refrigerant loss can indicate that a leak has allowed air into the system. So if you hear that thing running a lot, typically you're going to have a leak. The air is getting in there somehow. And with these things running in a vacuum, smallest little leak, it sucks air right in. It's really different than a high pressure or a very high pressure system. The leak is you're losing the refrigerant. It's leaking it out. With low pressure systems, a leak is you're bringing non-condensables into the system. Your refrigerant stays there, but you're bringing non-condensables in. So the purge unit purges them back out. If it's running constantly, you're bringing a lot of non-condensables in. You gotta find it and fix it. High discharge pressure is also an indication of air in the system. Just like nitrogen, oxygen is a non-condensable. It does condense, but it's under high pressure, high temperature. it will turn to steam and all that. In a system, it's going to be a non-condensable. It's going to stay as a vapor. Excess of moisture collection in the purge unit can indicate tube leakage. Again, if your tubes are leaking, water is going into the refrigerant. Just because your refrigerant is at 8 psi on the high side and a negative on the low side, your water is probably at 40 or 50 pounds of pressure. So it's going to push the water into the refrigerant circuit. To protect the system from overpressurization, low pressures typically use a ruptured disc mounted on the evaporator housing. The typical design burst pressure for a ruptured disc is 15 psi. Remember that. That will be on the test. Where's your typical ruptured disc rupture at? This is something that just got added into them too, the safety part of it. Additional shipping and safety instructions covered in the core section of this manual, but ASHRAE Standard 15 requires a refrigerant monitor that will sound the alarm and automatically start ventilation of a system to evacuate rooms before refrigerant concentration reaches the TLV TWA, threshold limit value, time weighted average. A refrigerant monitor is required for all ASHRAE refrigerant safety groups. CFC 12, CFC 11, HFC 134 are code groups as A1s, and R123 is a code group B1. All refrigerant systems must be protected by a pressure relief valve, must not be installed in series. Just like we're talking about regulator or nitrogen regulators, they now got to have safety relief valves on them. Can't install them in series. Can't install these in series. You can put 3 or 4 of them on a system, but they got to be separately out of the system. They can't be in line one right after another. All right, I'll take this. The next page is a picture. So this is what a centrifugal chiller looks like. This part right up here, that's the motor part of the compressor. This back here is your compressor. It's got typically they got 2 stages. You have your first stage, your second stage is just a big wheel. Is all that's in these things. It looks like kind of like you know what a turbocharger looks like. You got a flat disc with vanes on it. This same thing. The vanes pick the refrigerant up and just push it on. If it's only needing a low load, typically just the front one's spinning. It pushes it past the second one and one down in. If it loads up, they both start spinning. Down here, with this being with your compressor setting on top here, this would be the condenser side of the system. Back in here would be the evaporator side of the system. The picture they're showing down here is the same thing, but they're on top of each other. Instead of tubes being side by side, they're stacked one on top of each other. The top one up here is your condenser, bottom is the evaporator. You look, you can see all these little tiny holes right there. That's the hose that the water is flowing through those holes. So there's a bunch of little tubes in there. Water flows through those tubes. The outside part of the big tube has the refrigerant flowing in it. So the refrigerant flows across the tubes with the water in them. What he's doing is what they call punching the tubes. It's a machine, and you just run them through there, and because the water builds up chemicals and
That's why I'm clean to keep the system.
lime and all kinds of stuff in there. And you run that little machine, it's a little spinning brush. punch them in and out. Our service guys hate doing this job. I mean, it's an all-day job because some of those will have 200-300 tubes in them, and they're 10 foot long. You're just there all day long, punching them in and out, trying to keep them clean. Basically, the same way down here on the bottom. It's all tubes too. That's the tubes that your chilled water runs through, and then your refrigerant runs on the outside part of the tube. So if we flip this over to the next page, kind of a breakdown of a chiller. And you can look on it, you can see back part here is your motor right there. This is your compressor housing. Here's your first stage impeller. Right behind is the second stage impeller. So what that does, it sucks the refrigerant up through here. This is your return or your suction line. On the chiller though, the suction line is about as big around, like an 8 or a 10-inch pipe. It sucks that refrigerant back up through into these impellers based on if it's loaded up or unloaded. One or both of these impellers could be running. When it takes them, it pushes that liquid or that gas now down into the first part, which is your condenser. You can see your water coming in here, going through these two little tubes. But there's probably 100 or so of those tubes that's going through. Works its way up through there, comes back out here. Comes in at 85 degrees, comes back out at 95 degrees. You pick the heat up out of that refrigerant, condensed it basically to a liquid. From there, it then just drops down into here. They don't use this much anymore. This was using a float type metering device. But typically this bottom down here is going to be liquid refrigerant. It's just sitting in there, boiling off, turning to a vapor, working its way up through across these tubes, getting those tubes nice and cold. You can see your water coming in at 65 degrees, going through here, coming back out at 55 degrees. You drop your water temperature 10 degrees, just in that little short span. So this part, normally, this part here, you won't be able to feel that tube. It's usually covered with about 3 inches of heavy black insulation. It's 55 degrees, it's nice and cold. The top one is usually open, just metal. Usually runs around 95 degrees, 95 to 100 degrees. So there feel it's nice and warm. That's just the condenser side of it. This part right here, that's your rupture disc. That little disc right there. And it just goes up and vents out of the room, out to the atmosphere. It typically runs up to the roof somewhere. It vents off. So if you're sitting down here and you've got a bunch of liquid refrigerant down in here, this part's running at 10 inches of mercury. And for some reason, you dump a lot of hot water on that tube, you get it in there, you run that refrigerant up, pressure up above 15 PSI, that disc is gonna bust, and all the refrigerant from in here, right up here, at the roof. So you don't want to do that. And it's really, this little connection right here is where your purge, that's where your purge unit would sit. They don't have a purge unit on here, but that's where the purge unit would connect to. It's the highest point in the system. Any non-condensables are going to migrate their way up to the top of the condenser, and the purge unit's just going to pump them off a bit and get rid of it. Pretty much it for chiller. Alright, anybody got any questions on type 3? Read it, study it, learn it. We'll take a type 3 test next week, and then we'll review from the core the whole way through type 3 after the test. The following week, we'll take the entire test. Probably take a good hour and a half to take it. Alright? See y'all next week. Yeah, let's see if I got your syllabus in here. I can give you the number here. I don't have his number. I don't have Jerry's. But I can give you what the CN number is.
Because I wanted